And just a reminder to you, the presenters, you have to tell me next slide or something like that, or next animation step when I'll have to move on. Yeah. I hope I don't get confused. So, but just call me out if I get.
Thank you everyone for joining.
Hi, this is Claudia. Hi, Claudia.
Hi, Stefan. Good to see you.
Good. Yeah, what a shame it's not live.
Yeah, and thank you to all panelists to join this panel. It will be great, I'm sure.
Thanks for the invitation, Claudia. A pleasure.
Yeah, thanks.
We are on time. I think we can start.
Okay, ready to start? Then welcome all to this panel, Knowledge Graphs for the Physical World, What is Missing? It's my great pleasure to chair this panel, and it's motivated by some observations about what's happening currently in research. It's about vehicles becoming autonomous, whether that's like small shuttles, like in the upper left corner that are about to go around our campus here in Stuttgart, whether it's autonomous flying cars that go around that shouldn't have a pilot because that would be too much baggage, which is unnecessary. On our campus, we also have these sort of like almost autonomous e-scooters, and we work with some companies who want to have autonomous ships that even collaborate in order to tug big boats that cannot steer in shallow waters on their own. So there is a bit of autonomy of vehicles. And of course, they need to know something about the world. We, semantic web people, as knowledge graph people, we describe the world. Then I'm currently quite often asked about people who are interested in shop floors, in engineering, and they need to know something about the world. They need to know how to produce products, how to ship them along in the factory on the shop floor. And people talk about digital twins. I think we need to describe these products that are under development very precisely. And how do we do this? I guess we should do it with some semantic web technology, with some knowledge graphs. Together with colleagues, we work on some initiative towards a production that serves a circular economy. What is a circular economy? It's not only that you take raw materials, you produce, you assemble, you have service and operations, and then this is shipped to the customer. It's that you repair, of course, that you recycle, of course, and when you talk about recycling, what you do is you go from the customer back to the raw materials, but that you also recondition used products for new assembly into complicated outcomes, complicated products, and that you remanufacture. So you disassemble used products for their parts to be used anew. Currently a very niche market because it can only be done with by people, but in the future might be done by robots. Or what happens here at the University of Stuttgart, that we simulate all aspects of the world. For example, we simulate what's happening underground. The ground on which we step is a resource. It's a resource for storing heat, for storing carbon dioxide. But it's also a very critical resource because if something goes wrong, we may produce dangerous outcomes. Maybe gas might leak, maybe some of the ground may be warped, and some of the houses that we have may become broken. So actually, I can point you to sites where such kind of failures have happened. And the problem, of course, is that we need a lot of knowledge about the world then to be able to simulate it and to understand these dangers that could ensue. And of course, we talk about developments of digital health, and there we need to know exactly what are the machines doing, how do they help people. And these are just a very few examples of developments where new devices or new installations or factories or large production chains interact with the world, and where they need knowledge about this physical world. This physical world is often not quite the same with the kind of information where we started in the semantic web world, which often was more abstracting information. Yeah, remember like some of the first applications being about very simple registries about people and their interests. Here we have particularities of the physical world. We need to know about geometries. We need to know about physical measurements. We need to know about the uncertainty of certain properties that may arise from these uncertain measurements, or just because we cannot observe them. If it's something is underground and we don't know exactly whether a certain rock formation is there or not. We have dynamic objects. The people are moving around, the vehicles are moving around. The properties that they exhibit change. The properties are protracted over time and space, and the typical knowledge graph representations at least still have problems with reflecting this dynamics. Many of them, or all of them that I actually indicated now, are safety critical and may endanger people. And all of them do not just talk about a single system, but all of them talk about many physical systems that somehow interact and about which we need knowledge. Now, of course, there's always this question, to which extent do we as semantic web crowd ignore all these problems and just say, we store some data, let's other people deal with all these questions? And to which extent do we as a semantic web crowd reflect upon these issues, provide methods, and adapt to the needs of these environments? I don't know the answers, and that was my motivation for putting together this panel with a great set of panelists, and I will introduce them one by one as they give their short statements. Just here for a short survey, Maria Poveda Villayon from University Polytechnica de Madrid, Ganesh Ramanathan from Siemens Zurich, Corey Hansen from the Bosch Center for AI from the US, and Michael Beetz from University of Bremen have joined us. And we will first start with a brief statement by Corey. Corey, I'm very happy to have you on our list. Corey is a research scientist at Bosch Center for AI, and he was an editor of the initial W3C semantic sensor network ontology. At Bosch, he's exploring the use of knowledge graphs and neurosymbolic AI for autonomous driving, which of course is one of those scenarios that I indicated here. And well, Corey also wanders around in the woods, and I hope that no vehicle hits you there. Please tell us what you're doing and what kind of challenges you encounter in order to make sure you are not hit by any physical vehicle in the real world.
I guess I've been lucky so far. You can go ahead and go to the next slide. Yeah, so as Stefan mentioned, at Bosch, we're exploring the use of knowledge graphs for supporting autonomous driving, more specifically with neurosymbolic AI application. So we work on things like entity prediction, scene typing, roadside recognition, trajectory forecasting, among others. And so first, I want to thank everyone who was able to come and join us during our tutorial on Monday and learn more about these topics in more depth. Yeah. You can go to the next slide. So when Stefan first asked me to start thinking about this topic of knowledge graphs for the physical world, I was reminded of this quote by Gary Marcus, where he says, you know, we need to stop building computer systems that merely get better at detecting statistical patterns in data, and start building computer systems that from the moment of their assembly innately grasp three basic concepts: time, space, and causality. So this statement resonates with me. But I think if we want our AI to understand these concepts, maybe first we should understand how to represent them. So you can go to the next slide. And so I started looking at my own projects, to see, how are we representing spatial information, for example. So we have coordinates and we have regions. We're representing distances, angles, and directions. And luckily, we have some good tools and encodings for representing this knowledge. So we use GeoSparkle for coordinates, well-known text for geometries, and we have some theoretical grounding in region connection calculus. For time, there's a similar story. So we want to represent time points and intervals and ordered sequences. And there's a good set of languages and encodings, right? We use XSD datetime for timestamps, outtime for intervals and orderings, with some grounding in the Allen's interval algebra. But what about causality? So you might think causal relations are fairly simple, right? So if we look at the example on the left, we see, there is a road sign that may be causing the vehicle to stop. There's also a pedestrian, which may also be causing the vehicle to stop. But these relations are not the same, right? One of these is going to have a stronger causal effect on the stopping vehicle than the other, right? So these relations are weighted. And second, causal relations can be complex, right? And what I mean by that is not all relations are binary. So we can have causal relations between more than two entities. And so this kind of begs the question, so how are we representing this knowledge? And I'm purposely being a bit hyperbolic here by just leaving this section blank, because I know there's really good work in the semantic community on causality. But what I see is that there's a lot of work on extracting causal relations and less so on their representation. You can go to the next slide. Thanks. And so I wanted to highlight one project that I think is leading in the right direction. So this is work at the University of South Carolina, where they're representing autonomous driving data, first as a causal Bayesian network, and then deriving causal effect estimations. And to this point, this is fairly standard practice. But then trying to represent all of this complexity as a knowledge graph. And the example we're showing here is what's referred to as the mediated design pattern, which is representing the causal relation between the road sign and the stopping vehicle, which is mediated through a walking pedestrian. And this is encoded as a hyperrelation. Now, the details of this graph are out of scope, of course, but just to end, I wanted to stress that I'm very much looking forward to the day when we have, a set of ontologies, a set of design patterns and standards for representing this very important yet often neglected causal knowledge. So thank you.
Thank you very much, Corey. At this point, to the audience, when you have any questions, please feel free already now to add them to the discussion space or to the Slack, whatever you prefer. I will try to watch these two spaces. We will first do the round of statements, and then afterwards you will have the possibility to ask your questions to the panelists. So thanks again, Corey, and we'll move on to Michael Beetz, a professor for computer science at the University of Bremen. And he's leading a concerted effort called EASE, which is about providing robot and human activity data and letting robots help the human in everyday tasks. And when I asked some of my robotics colleagues, I knew a bit about Michael's work before, but when I asked some of my robotics colleagues about which robotic person would really work at the intersection of knowledge graphs and robotics, I would always be pointed to Michael and to no one else. So Michael, the floor is yours. Are you still muted, I guess? Still, we can't hear you yet.
Check the microphone settings.
So that's the demonstration effect, because before the panel started properly, we were already chatting. No.
Try to change settings on the Zoom. Maybe you have chosen the wrong microphone input.
Which is strange, because before, then I would suggest the following. How about Michael, you disconnect and try to connect again, and in the meanwhile we move forward with Ganesh. Okay, so hopefully see you back in a minute, and in the meanwhile we move forward to Ganesh. Ganesh started as an automation engineer and now has about 30 years of experience with roles in engineering development, more engineering rather than computer science, so maybe not typical for the crowd here. And he very much enjoyed bringing the Web of Things approach to products and systems at Siemens Smart Infrastructure. And I was very impressed when I talked to Ganesh at ESWC this summer, and only learned now that he's actually the only PhD student on this panel. So Ganesh, please share some of your experience from your last 30 years, or from your PhD student time.
Thank you. I hope one doesn't affect the other. Yeah. Good. So actually what Stefan and Corey said makes my job much simpler in describing the use case that we have. So at Siemens in specific, I'm at a group where we are investigating how can knowledge graphs, how can semantic technologies in general help us make smart infrastructure truly smart. So next slide, please, Stefan. Good. The trouble starts already with the title. The smart infrastructure hides a lot of complexities underneath by naming it as smart. Because infrastructure by nature, they are composition of systems, and each having discipline-specific, sub-discipline-specific knowledge behind it. So even if you just take a building as a smart infrastructure, you see things like heating, ventilation, security system, fire extinguishing, energy management, renewable energies, and all this are clubbed under one very convenient title called smart infrastructure. So now when we want to think what would be a digital twin of this infrastructure, so this becomes suddenly a very imposing question, a very challenging question. Next slide, please, Stefan. Stefan, could you?
Oops. Yeah, so now
exactly.
We're stalled.
So I wanted to use this image, which is always ringing in my mind. So René Magritte painted this picture and called it "This is not a pipe." And in his very philosophical discussion about this, he said, can I smoke it? Can I smell the pipe? Can I feel it as a pipe? No, so and I think this rings a lot of facts which are related to what we call as a digital twin, because once again, the term digital twin hides behind it or actually oversimplifies some of the complexities that you need to tackle. Next slide, please. And so if I say like what would be our twin? So considering smart infrastructure, well, what would be a basic minimum twin that I can deal with, I can talk to, I can interact, I can understand its behavior? So even if I tear down the aspects behind the smart infrastructure, we see three aspects, at least the key aspects. So one is what we very often see and tackle. This is the structural aspect of it. We describe buildings, we describe machines, factories, production lines. So we describe the structure and composition of the system. So we tackle system design, knowledge graphs to describe system design. So this is very visible. But what is less visible or what is less tackled are these two other aspects. Systems obviously have some form of control and coordination going on behind them. So that is this automation system. So it is a piece of program, a software designed by the automation engineer to do the job. But how well is this described? Or how well does the automation system know what it controls and coordinates? And then the third aspect, which I would like to point out, is like there's also the physics behind the whole world, right? I mean, what is a heating system? How does a room get lighted up? When you supply so much energy of luminescence to the room. So things behind the physics, the behavioral models. These have existed for a long time, but its integration into a cohesive knowledge graph is still to be kind of visibly seen in the industry. And why do we need this? Because between these pillars, you also achieve use cases. You are able to validate your design, you're able to detect faults, and then you're able to optimize the entire performance of such infrastructure. So that's our wish for a twin. What would a twin actually lead us to are finally these use cases. Next slide, please, Stefan. Good. So taking this wish forward, if you ask what would a knowledge graph look like? So take an example of a room. Maybe the room there where you're at the moment. So how would you describe it with a knowledge graph? So this pictorially puts it, here is a room located in a floor of a building, which is now being heated and cooled using an equipment regulated by this function. And these are the data points, the final IoT constructs of a data lake that expresses the state of the system. So a knowledge graph, when it cohesively brings all these multiple dimensions together, so that's where the real twin is born. Next slide, please, Stephen. Good. But however, the challenge, that's easier said than done. This picture just shows even a bare minimum building automation system with all its technical systems. You have levels of functional hierarchy, discipline-specific functions that are put into it. So given such an heterogeneous systems, next slide, please, Stephen. Given such a heterogeneous system, when we attempt to create a description of the thing, Stefan, I think one slide got missed in between. Yeah, exactly. So, yeah. So, given such a system, when as ontology engineers, when we attempt to look at this, okay, we can already identify these layers of abstractions, beginning from the most abstract structural knowledge about how things are organized, how things should work in general, from, for example, what is a lighting system, what is a heating system, and then down to the nuts and bolts of how each product and systems are done. So one way of approaching it is to just try and abstract the complexity. Like the deeper you go down in this one, more usable the ontologies become. And when we couple this, that all the use cases that we saw, like the structural knowledge, the knowledge of the function, the knowledge of the physics, they are contained in between the layers when they are linked with each other. To the final slide, Stefan. So what do we have now? There's been an enormous amount of work in the semantic community to address this. but they all are happening in these islands, so like there's a great many people working on describing locational aspects, people working on describing system designs of say buildings, of HVAC systems, and so on. People who work on describing very low level network protocols. But the first thing that we see here is, wait a minute, I mean, these are all individual islands of work. And for my twin to be born, you need these islands of work to come together. So first of all, like that these ontologies work together, that interoperability needs to be established, so that like I have one cohesive base of information to model my knowledge on. So this is what we see in smart infrastructure as what is missing, and it's a challenge for future research, is to bring all this knowledge together, link these multiple aspects, not just structure, the process, the controls, the programs that run. Yeah, so with that, I give back over to you, Stefan. Thanks a lot.
Thank you very much. So now let me introduce Dr. Maria Poveda Villalón. She's an associate professor at the AI department at Universidad Politécnica de Madrid, and is an expert in ontology engineering, having worked on methodologies and contributed to standardization bodies such as W3C and ETSI, and likes to stress herself, not only with work, but also with hobbies like scuba diving and swimming. So Maria, what do you have to say as ontology engineering experts to the challenges put forward by the others?
Yeah, thanks, Stefan. So, well, when you asked us to talk a bit about our background and how it is related to the open challenges in the physical world, I wanted to introduce myself as a researcher, but I also participate in many projects where I act as an ontology developer or ontology engineer. And then I wanted to take advantage of this panel to speak about my almost everyday problems, and they are not really related to the physical world, maybe in the sense that it is oriented in this panel, but to many more realities or many more words. So at the end, our problems about ontology engineering. And I guess they are not even new problems, and probably most of you have been seeing this for a long time. So, well, in these projects or in my research, I get to develop the ontologies, but also to work in the evaluation techniques, publication, conceptualization, and in general, generating also knowledge graph and contributing to the semantic web. Sorry, so next slide. And for doing this, I use mostly as building blocks my computer science background. I'm a computer scientist, and also had a lot of knowledge or experience in knowledge representation. Next. So that is what I built on top. And which is my real world or physical world from the ontologies that I developed. So some domains are Web of Things, sensors, like the Saref ontologies, Ganesh just mentioned, ontologies about information technologies, like, I don't know, tracking system, GitHub, GitLab, and these systems that they generate a lot of data, video games, and so on. And those are very close to my background because they are related to computers. But I also have to work for other domains like agriculture, sign language, videos, patient safety, insurances, environment, buildings, and many domains that I'm not an expert at all, and will be impossible to become an expert for every project. And then next. And for building these ontologies, the other bricks or building blocks that I use are the methodologies that are out there, or the tools that we have developed in the semantic web community, the languages that we use, and the specifications. Next. That is from what I use, but I also have to read manuals, APIs, data samples, and so on. And most of the times, and when we are more lucky, we also have domain experts, so that we are able to transform their knowledge about their domain, that will be their physical or not so physical world, that they want to represent in our ontologies or in our semantic models. So in the next slide. So almost in any project, we will have this landscape, like the ontology development team will develop some ontologies or models or vocabularies, and someone will need to understand them. Probably users that most of the time are developers, maybe developers in terms of generating knowledge graphs, or developers that needs to understand the ontologies, maybe to build a interface based on the model behind, and so on, or to annotate some corpus or data. In some cases, in most of the cases, we also have domain experts that may want to build the models themselves or with some help, or support us in building the semantic models. And in that case, it is very important to see that we need to really establish the communication, because we might be using the same terms in different ways, or we might be using different terms or concepts to relate to the same things, and we really need to work in that communication with the domain experts. Also because sometimes they use their own symbols, their own diagramming systems, and their own notation. So we really need to work on that. And also there are newcomers that can be people who is joining the ontology development team, or people that they need to build a lightweight model at some point. So in the next slide, so one thing is that either the users, the developers, the domain experts, and all the newcomers will need to understand to some point our tools, languages, and specification. And I wanted to link here about this point about the specification, related it to Carl Hammer's keynote at the workshop on ontology patterns on Monday. And we were talking there about the W3C recommendation. That is this, we have these 6 or 7 documents describing OWL down to the last details, so that there are no loose ends. Everything is greatly described there, but how much does it cost to learn how to read these documents, how to understand them? And by the way, I'm really thankful for the W3C documentation about OWL, and I'm keep going back to it almost every month to check the details. But how can we extract what is needed from there, so that the learning curve for users, someone that just need to make use of an ontology or RDF, so domain experts that just need to build a lightweight ontology thinking about how it is going to be represented in a graph, or newcomers can enter and make use of our languages and tools in a correct way. Also, as going back to the users, we need to communicate better. We need to communicate better the ontology, so that the user and people exploiting them understand the code or the documentation quicker. And not only them, but also us when we want to reuse some other ontologies, as Ganesh was also showing a landscape of existing ontologies in his presentation. I'm hearing in many events these days or the last year about the lack of good visualization, either for reading, for understanding ontologies, and also for designing ontologies in a graphical way. Also, going back to how do we lower the learning curve for newcomers and domain experts, I have also another question, that is, to what extent do they need to understand our implementation languages? Which parts should be transparent for someone who is not really in the core of the development? And finally, I think domain experts' time is precious and it is scarce, and we cannot have a domain expert with us all the time. So we need to get the right answer in order to make the right modeling decisions in our ontologies or models. If we need the right answer, we need to make the correct question. So how does a newcomer learn how to make the correct questions to the domain experts? So so that when they explain something, which are the questions that leads me to use one axiom or the other? And what are the first
Maria,
steps?
we have to look a little bit at the time. Yeah.
Yeah, so that was my last question. And in the next slide, I just wanted to say thanks, and also thanks for the icons I reused. Sorry.
Okay, so thank you very much, Maria. Now, Michael, you are back.
I hope it works.
And we hear you?
Okay, excellent. Cool.
Yes.
So thanks a lot for having me. And yeah, so my research topic is autonomous robotics. So I'm investigating robots that do everyday manipulation tasks, preparing simple meals like making popcorn and things like that. And I might be a little bit of a robotics chauvinist, right? So thinking that robotics is the most important topic in AI. And yeah, I want to talk a little bit about why I think that robots need knowledge graphs and vice versa. Next slide, please. So if you look at robotics, right? So kind of the most important thing is that you give autonomous robots very vague tasks. So you say something like clean up, set the table, bring me something to drink, right? And the job of a robot control system is to compute a body motion. And a body motion, which is essentially the voltages you give to every motor in your body, that achieves the desired effects and avoids the unwanted side effects, right? And everything that is in between that very vague task request and that very concrete body motion has to be in the knowledge and in the reasoning of the robot, right? So that cannot be kind of another place where this takes place. So when Cory was actually talking and taking that quote by Gary Marcus about the importance of time, space, and causality, right? You can think about why this is important. And I would basically answer it's important for one reason and one reason only, then that is you want to act in your physical world in order to achieve your goals. And for that, you have to reason about time, space, and causality, right? And so it's extremely central. Next slide, please. So to just get an idea about what is the kinds of things we have to represent, right? So you can just look at one category of action in that robots might have to do, something like pouring, right? And the big challenge is that in an open world, you have to write a robot control program to pour any substance from any source to any target and for any purpose, right? And it's kind of a huge space. And there are basically very specific pouring tasks like neutralizing acid, right? And for that, you better have some knowledge about chemistry before you do it as a robot, right? Or extinguishing fire, watering plants. So essentially, this kind of information you can get through knowledge graphs you build by basically building robots graphs on Wikipedia and other places, right? WikiHow and places like that. But also kind of another dimension of autonomous robotics is that you want to have robots performing very different tasks in very different environments and with very different objects, right? So when you want to have an outdoor robot, you want your outdoor robot to connect to OpenStreetMap, to kind of get background knowledge about its environment, and you want to get it in lightweight way. So yeah, so that's kind of why robots need knowledge graphs, right? So next slide, please. So for me, kind of knowledge graphs need also robots. And the reason is that if you're looking at text knowledge, it's at a certain abstraction level that actually lacks our vision abilities, that lack our physical experience in the world, right? And for that, you have to be, you have to have a system that is embodied. And robots are the way of embodying it, and kind of logging the action data of robots in experience files is actually the way to get the common sense, to get the intuitive physics understanding that is not contained in any explicit knowledge base. Thanks. Next up, please. So what is missing? So for me, I think one of the huge opportunities we have, and this is kind of shared by many of the, by all the readers before, is digital twins, right? And I think virtual reality has that huge advantage that in the scene graphs, we have complete representations about the world at a level of detail at which we act and perceive the world, right? And with these scene graphs, we have rendering engines, which basically directly connect to the perception apparatus to robots. And we have physical simulators where we basically can simulate the motions that we have computed in the world and see it. So this is kind of the scene graph is for me an implementation for knowledge representation system that that has a potential of directly connecting into the perception action loop of robots, right? And if you think about it, then you want to have the scene graph representation of what the robot needs to know about its environment. Kind of, you want to link the scene graph representation into an ontology, right? So that everything that is in the scene graph is given a semantics, it's machine interpretable and machine understandable. And if you have that ontology, you just want to go out and build your knowledge graphs and connect it to this ontology, right? And by doing that, it should be possible to actually make the knowledge that is available in the web but abstract, connect it to your robot control system and make it actionable for robots. And I think that is, for me, the dream where I like to push and where I would like to kind of connect the communities of robotics and knowledge graph together. Thanks. So that was my statement.
Okay, so thank you very much. Let me move to the end of this presentation. Thank you all for your statements. This raises for me really basic, important questions. A question to all of you. You talked about autonomous cars, robots, or digital twins representing buildings. Do these need a kind of awareness of themselves? So when I talk to my control colleagues, they develop wonderful systems that, for example, keep the e-scooter upright. But when do these systems, when is it not sufficient for these systems to just do this action, like keeping them upright or keeping the robot walking? When do we have to add a kind of a self-awareness, knowing which behavior is required? That's a question to all four of you, but I don't know. Michael, do you want to go first?
I could try. So for me, I think it's a question of where it starts. I think where it's absolutely necessary if we want to have intelligent systems jointly working with humans and learning with humans, right? At that point, It's not sufficient to have a kind of a black box system that provides a policy, yeah, input-output kind of relation. But at that point, a system has to see when a human needs help. It has to reason about whether it's capable of providing this help. It should reason about how it can provide the help and how to synchronize, right? And at that point, this is for me not possible if you don't have knowledge representation and reasoning and deep models underlying these systems, right? So that requires introspection, it requires self-programming, and I cannot imagine that being able without kind of the methods for knowledge representation and reasoning.
Okay, thank you, Michael. Ganesh, you want to jump in here?
Yeah.
From your point, does it only apply to robots or also for buildings?
I think I feel buildings are more troublesome, but that's because I deal with buildings. Things are hardly static, you know. I mean, the reason why systems need to be knowledge aware is purely because environments are so dynamic, so unpredictable, you know, and not just the environment in which robots or buildings live, but also the systems that support them. For example, if in this room I put one more lamp, I put one more radiator, I change the regulation of how much heating this venter should be accomplishing, regulations during COVID times for ventilation, these changes like attacks all perspectives, right? And in a very short thing, I believe knowledge-aware systems is the way out, or is the only way out. Thanks.
Okay. Maria or Corey, do you want to?
Question
Please chip
slightly.
in.
So you mentioned required behavior. Maybe I would change the word a bit to say acceptable behavior. And when we think about autonomous driving, for example, you know, since we've been driving vehicles, we've been developing rules and regulations and laws about how these vehicles should behave on the road. And, you know, we can represent these laws and regulations in symbolic form. Yeah. And so, I mean, I'm of the opinion that, you know, we don't necessarily need to relearn these rules and regulations using, for example, subsymbolic or deep learning techniques, but rather we can represent them into knowledge graphs and then utilize these knowledge graphs to infuse them into our AI systems. Yeah.
Now, I mean, you posited, all three of you, that we need these capabilities and knowledge graphs should be the answer. But what would it require from the knowledge graphs? Are the current knowledge graphs ready to do this? Maria, what would you say on that?
Yeah, I was going to comment on the point before, but it is also related to this one. So maybe what we should analyze how to integrate in the knowledge graphs, as we have now, is the systems for the truth maintenance. I don't know if I translate it correctly, but in other logics, you have these systems for whether new knowledge keeps the knowledge before still true, or you need to update that. And up to today, I haven't been always working with rather static data that didn't even have this problem. So whether to keep the truth and evolve the knowledge and temporal reasoning, I think that we are not really far in this community in that regard.
Mm-hmm. I think I would agree on that. So we have some questions from the audience. Neha, do you want to speak out?
Sure. Thank you to all the panelists. It was really a great insight. I had very quick questions. So I had three, and you can choose like if you want to answer any one or all the three, or in whatever fashion. So I know all of you did touch upon how KG is helping in each of your scenarios, But one thing that we always look is like, why are we using KG and not something that is already existing? So was there a particular reason why you thought that, oh, KG can actually be helpful and above anything else? Or was it just because KG is into a fashion now and everyone wants to use it? So that was the first question. The second is like,
maybe we let them respond to that first, Neha?
Sure.
Yeah. So is it just fashion that you all go for knowledge graphs, or who wants to go for that?
If I can just quickly go, because
Yes.
this was a question in like early 2000, like mid 2000s that I faced. Building automation has been around for ages, and like people have developed ways to present knowledge, proprietary manners, even pure relational database contained knowledge. And then GraphQL was suddenly there, and people said, "Why not GraphQL?" And then I was evangelizing RDF and reasoning and graph data and all. But I think the change comes when one thinks that it's not about representing knowledge that you have, but also link against knowledge that exists there out in the world. So, for example, the turning point came in a big way when we realized, oh, wait a minute, building information models, they are generating knowledge. Oh, look, energy systems, they are generating knowledge. And what happens if all of them do it in their own proprietary manner? So that's where I think the standardization coming towards knowledge graphs using technology and standards, that's a massive convincing factor for us. Yeah, so that was on your question one, but an excellent question. Thanks.
Neha, next question.
I see. Okay,
I can maybe add to that a bit.
Or maybe Corey, yeah.
At least for us, knowledge graphs are a great tool for knowledge integration. And for example, with the scene graphs that even Michael mentioned, we can integrate information from autonomous vehicles, from the cameras, from the LiDAR, and detect objects and events. And that's fantastic. And that's the information that people typically use. But with knowledge graphs, we can integrate other types of domain-specific information. Like we can pull in information from OpenStreetMaps about surrounding buildings, and we can integrate conceptual knowledge, common sense knowledge from ConceptNet about the relations between the objects and events in a scene. And so the knowledge graph serves as this kind of unified model for integrating all of this type of information. I think it works quite well at that task. Yeah.
I see. Thank you so much. That really just helps me confirm that, okay, what we are doing is correct. The second question, because I'm a PhD candidate and this is the question which I've always been asked upon, be it conferences or just like discussions with my committee. So can you shed some lights on what are the evaluation methods or techniques that you are maybe currently using or you plan to use for the knowledge graphs that you're creating for the work that you're doing?
I really like this question because, yeah, it's sort of easy to build some knowledge graph and then claim something magic happens. But how do you even then in such complicated scenarios clearly demonstrate the added value? Who wants to take a stab at that?
Can I again go with my boring building example? It's not as fancy as robots and self-driving cars, but one of the evaluation, one of the validation thing is, would a human engineer who's used to these classical engineering artifacts of knowledge, would this engineer find the same answers when looking towards a knowledge? So, for example, let me take the requirements of a building, electrical systems, and all those requirements are in all those hundreds of pages of paper documents. There they are. And from some magic, I've translated that into knowledge graph here. Okay. So to me, the knowledge graph achieves its goal that if I can ask a question here and I find the reasonably right answer here, as well as the same answer here, or even a better answer here. So I could ask a question here, which boiler heats this room and what fuel supplies that boiler. I'll have to go through these pages, I find the answer. And if I look at the knowledge graph and I ask the same question, is the quality of ontology engineering good enough to capture these aspects, the structural, the physical, the control aspects? And to me, as an evaluation, at least for the building domain for smart infrastructure, it would heavily rely on validation of human experts to do that. Formalization, probably, but I'm not there yet, at least till I finish my PhD.
So I guess one issue that, let me try to translate this also, there are different aspects. One is like you have a product and you evaluate. The other is you're a PhD student, yeah, and you want to write papers for the Semantic Web Conference. And can you show an advantage with your limited means in these areas? Or can you just say, okay, I developed something, but I'm not quite sure whether it now is really better, without asking the 50 experts that I don't have?
Yeah, I think asking the experts and putting that as a validation in a paper would never work. That you probably need some automated reasoner to kind of like synthesize questions, know the answer and validate the thing. So sounds very fancy, very, very interesting, but I'm sure there are clever people to tackle that.
Michael, you have been on the academic cycle more than and integrating knowledge graphs into robotics. What kind of scientific validation can you provide that what you do is not just like helping a single case and then one claims that the knowledge graph has specifically been built for this single case, but that you achieve a level of generality sufficient to convince your robotics colleagues that what you're doing is good work?
Yeah, so I think it's the key is what questions can a robot answer, and basically are these questions that the robot can answer sufficient for performing the actions in the right way, right? And if you are looking at that, so the way I would suggest to evaluate it is the same way as we do it in pedagogics, right? So there is kind of the taxonomy of different levels of understanding that starts by just remembering things, then goes to understanding, then being able to transfer what you have learned from one thing to others, to evaluate and kind of construct. And I think in some ways you kind of want to show that if your systems actually acquire knowledge by building knowledge graphs, they can kind of climb that ladder of different cognitive capabilities and be much more competent, right? And I think that would be a kind of a way of evaluating it that kind of you want to do from the inside, right? So from the scientific point of view, what is again in cognitive capability that you can achieve by building knowledge graphs? Yeah.
Yeah, you had a third question?
Yes, but just synthesizing what I heard, and hopefully I heard it correctly. So it means like we are just looking the evaluation method as a knowledge graph. Can it answer my question? So it's becoming a question and answer kind of a domain more of, and maybe I'm wrong, and maybe it's just one part of it. But whatever Michael was telling at the last, it takes me to my last question of the accountability that we are adding to it, because be it like buildings that you're working on or the robots, the autonomous robot or something, we all know like at some point, because it's the work that the human is doing, it can fail. So who will be accountable? How do we make sure that, because we have already added provenance to say that, okay, where the information is coming from in knowledge graph, but how can we make sure that accountability is counted when knowledge graph is used to elevate something or build something? Does that make any sense? Sorry.
Absolutely. It makes a lot of sense for me, this question. Maybe Maria, could you say something on the ontology part of accountability, and then some of the others could chip in to talk about the system aspect of accountability.
Yeah, so well, I was actually thinking that this could be the most difficult question, because how can we make it really sure of this, apart from what you already said about adding all the provenance and keeping track of all the facts and travel of all the data that we want to track between system or stages or steps or so on. So at the end, I guess you will be ending up with a way more complex knowledge graph to take all this data, and I don't know, I wouldn't know how to measure which is really the best way to have it.
Okay.
So do we always need them?
Thank you. Someone else wants to chip in on accountability, Mita? Yeah, please do.
Yeah. So I think from the robotics point of view, right? So I think you would take knowledge graphs as for building hypotheses about actions for achieving a task, right? But then you would actually, before executing the action, you would simulate it in the digital twin in order to see whether the plan you kind of have computed makes actually sense in the physical model you have underlined, right? And so you have to make sure that the digital twin models the world kind of realistic enough, but I think for me the knowledge graph is more for generating hypotheses for actions, but then you would test the hypothesis by mentally simulating it and see whether it makes sense at all.
Thank you. There's another question by Valentina. Valentina, do you want to put it forward yourself, or shall I just read it? Maybe that becomes a little bit complicated. So let me just read the question. Are the knowledge graphs sufficiently rich to support the decision-making for interaction and cooperation protocols? So, I mean, the question, of course, is, yes, we want to have these kind of insights, self-awareness, but can we even succeed with modeling the world? Or is it just like the world too infinite for us to really integrate the knowledge graph into these systems? Maybe, I'm not sure I translated correctly from the writing, but that was my interpretation from what I read. Corey, how is this for autonomous driving? I mean, the world is so big, right? And there's always the long tail of things that one doesn't know about, or at least I remember the car I sold today. Yeah, it still got the old map and didn't know a couple of things. And of course, we get more up to speed and more up to sync up with the real world. But will we ever catch up with the most recent state?
Yeah, I'm somewhat reading this question similar to a previous one about, how do we determine the quality of the graph? Yeah. And I guess for this, at least within our tasks, the quality of the graph manifests itself in the quality of the downstream task, right? So in Michael's work, it's the actions taken by the robot. For example, in our work in perception systems, it might be the ability to predict or detect an object in a scene. And so if we can add, if the knowledge graph improves the detection capability of our perception system, then it's doing a good job. If we can add additional knowledge to our knowledge graph, and that further improves our perception and our ability to detect new entities, for example, then we're doing even better. We've actually found that adding information to the graph actually detracts from our ability to detect entities. So that's also true. But at least that's the case for our projects, and that we're typically looking at the downstream AI tasks and analyzing them to determine how much or little our knowledge graph adds to the overall equation.
Thank you. Valentina,
Yes,
does it satisfy you?
Being
maybe you...
unmuted. Well, actually, the point was more having dubbed in the multi-agent systems and autonomous systems community. There's not just a notion of how, what the agent sees about the world, but there's also what the agent sees about other agents and how they can interact together. So the issue is, our knowledge graphs, can they be sufficiently rich to support, and it's in a way similar to what Michael was saying earlier, to basically support the formulation of hypotheses or plans that then support the cooperation, the autonomous interaction between the different agents. And so we should also be aware of this other aspect that is important in certain other communities. And I think we have a sort of responsibility if we want to, our knowledge graphs and our way of representing knowledge to be taken also by these other communities that are looking more at the notion of distribution.
Stefan, may I just...
yes, please go ahead.
That's because, Valentina, my research also targets using multi-agent systems for building automation. And one example is like you have these systems which need to interact with each other. An energy consumer and energy producer, they need to interact, but they also need to know the protocol, the communication and coordination that they need to establish. And then comes, what are the obligations and commitments that these two agents have to respect to enter into this coordination protocol? And I think that's an exciting area of work. How do you describe these protocols and commitments so that the agents can look at it and say, yeah, I would like to talk to him, and then I can do this, and I can enter into a supplier-consumer relationship and commit to things. It's I think a great topic for knowledge graphs. Thanks for bringing it up.
So thank you very much. So at this point, I'm reminded that we're already 5 minutes over our allowed time. And so I'm very sorry, because after some hesitation, now the questions come in. We'll have to stop here. I want to thank you very much to all the panelists.
Stefan, if you want, you can take, let's say, 10 more minutes. If
10 more minutes, okay. I'm happy to.
If we don't lose attendees for the closing ceremony.
Okay, then I'm happy to do so. Yes, absolutely. Okay, so Valentina, was your question answered, or?
No, it was answered. I was just going to add to Ganesh that this community a long time ago started looking actually at the explicit representation of protocols, but then we kind of lost it in the way. And we focused more on the more static side of the knowledge that agents need. Maybe we should go back and revisit some of the ideas because the problem is that if these protocols are static and need to be known in advance, there's very little cooperativeness that is possible. And maybe we should look at how our knowledge graphs can also help us to share a little bit of these interaction protocols. I know that of some work that is done in this area in the multi-agent community, but a little bit more of mixing and matching, I think, would be useful.
Absolutely. I mean, one very emerging field is distributed renewable energy, which requires these interaction protocols. Absolutely a great use case.
Yeah, I think like some early semantic web scenarios started out with a lot of agents interacting with each other, and then several years later there was some paper, where are all the agents? Yeah, because as Valentina put it forward, basically we did much more database work where the database is static.
If I can add one thing, Stefan, very quickly, there was a Dagstall meeting in February 2021. It was virtual, and there's going to be a new version in person in February 2023. And some of these issues, I mean, Jim was there, some other people from our community were there, and people from the multi-agent system communities. And these issues have been brought back to the fora, and people are, starting to looking at this from a different perspective, and knowledge graphs play a prominent role in there as a way to basically give knowledge to the decision-making process for autonomy.
Yeah, excellent point. Jeff has put forward a question. Now, I'm not sure if he's already raised his hands to be included in the discussion, but let me read his question. What are the key challenges in knowledge graph construction in these different scenarios? Who wants to start on that?
Well, maybe I can give the beginner's answer, because I'm not an expert in knowledge graph construction, but when I have to do, most of the problems are about the tooling. If I need to combine cells and take decisions, then I have to program myself, because of the cell systems don't help much. And of course, validation, whether I'm generating the correct data and whether the answers are right. And again, here I need the precious domain experts to help me.
Someone else wants to complement that? Okay. Yeah.
So for me, one of the main challenges would be to get the knowledge graphs dense. So by that, I mean, it's kind of easy to answer questions, right? But when you have to generate actions, you kind of have to go all the way, and you cannot have any gaps in between, right? And the questions of, can we have knowledge graphs that can really go for all contexts all the way without kind of running into gaps? I think this is, for me, the biggest challenge, right? In particular, because lots of the knowledge is common sense and intuitive physics, and not stated explicitly in most of the places, right?
Jeff, was your question correctly represented and the answers, or what do you want to chip in on that?
Thanks, Stefan. I think in these large-scale scenarios, maybe automatic knowledge graph construction would be needed. So I would like to hear about, which aspect would be kind of more challenging to be automated, and will some of those validation techniques, like competency questions or other kind of techniques, used to help check the qualities and things like that. So it's more about automation. I suppose that if you have to do this all by hand, it won't be scalable to deal with all this fast changing world.
If I can chip in from the building and the smart infrastructure domain, there's like a vast heterogeneity of source data. So a lot of it just even on paper, diagrams. So for example, we are working on how do we even use computer vision to understand schematic diagrams and then generate the knowledge graph out of it, and that's already like a massive challenge behind that. So. Legacy data, if I can just use one word, legacy data for us is a huge challenge.
Yeah, yes, indeed. Obviously, I think there's lots of work about using NLP and CV techniques to identify the object, identify the relations, and learn the tuples. But in this kind of ongoing systems like cars and whatever, I think that it is quite challenging to. I mean, if the quality of the graph is not good enough. So which aspect do you think is kind of deserves more research in the coming years in this kind of automatic knowledge graph or tuple generation?
Any ideas about that? And this will also have to be the last answer, as we will have to move on to the closing session, but we'll still have time for one or two answers by the panelists. Corey?
Yeah, I'm not sure if I have a great answer for this in regards to the automatic knowledge construction. Just a comment though, I mean, I do see a lot of use cases coming up, especially around this topic of the knowledge graphs and agents in the physical world that require the representation of use of probabilistic knowledge. And this can be quite awkward or difficult to represent using our current technology. So if you're asking, where would we like to see future research, I would have to put this up as something that could be quite important. I know this was a topic of some research a few years ago, and I still think it's quite important.
Right, thanks.
Okay, some urgent last words. If not, let me now really thank all of you, all the panelists, all the audience for asking questions. There are more questions coming in now, but we still have to stop. So I'm very sorry about that. And thanks a lot for your contribution. And we will move on to the other room where there will be the closing ceremony of the conference. Have a great day. Bye-bye.
Great, thank you.
Thanks.